So let's solve this problem. Air enters a compressor at a given pressure and temperature and exits at a given pressure. The stray heat transfer and kinetic potential energy effects are negligible. Air behaves as an ideal gas. And then this sentence right here is key. Using variable specific heats that are basically accommodated or found. That's how table A22 is developed. It's developed using or accounting for variable specific heats for air. Answer the following questions. What is the minimum theoretical temperature at the exit in degrees C? And if the compressor isentropic efficiency is 90%, determine the actual exit temperature and the actual compressor work in kilojoules per kilogram of air flowing through the compressor, and then the entropy generation. Well, this is a long problem, and so what we want to do is sort of set it up that we have a compressor, comes in at state 1, out at state 2, and I know I like to try to avoid negative signs, so this is the power or work, so let's put m dot as the power into the compressor. And if we do a first law analysis for that control volume around that compressor, we find that it's equal to the mass flow rate of air through the compressor times the exit enthalpy minus the inlet enthalpy. Okay, that's a positive power in. And for like the answer for part C, a lot of times you just have this, the power divided by the m dot, and then it's just has units of kilojoules of work per kilogram of air flow through, and that's the right units. But let's back up. So this is a schematic of our compressor, inlet and outlet states, and we want to find the minimum theoretical temperature at the exit. Well, a property diagram and Mollier diagram or HS diagram is helpful. So we have two lines of pressure. This is our inlet pressure. This is our exit pressure, P2. And we're starting at state 1, and we're going to go up to state 2. And if we do it where it's adiabatic and reversible, then it's isentropic. So from 1 to 2s. And for air is an ideal gas, H is a function of temperature only, so lines of constant temperature are horizontal. It's a function of temperature only. So if there were irreversibilities, you would kick it up to the same pressure, that would be state 2, and it would exit at a higher enthalpy, hence a higher temperature. So the minimum theoretical temperature for an insulated turbine that is reversible would be isentropic expansion, or not expansion, compression through that compressor. So we say that the T2min is when S2 is equal to S1. All right, so we're going to use our table, and so if you do that, then the change in entropy, S2 minus S1, is S2 naught minus S1 naught minus our natural log of P2 over P1. And if this whole side is 0, because it's isentropic, and you know the pressures, P2, P1, you know the gas constant, you know the inlet temperature, you can get S2 naught, and then you can get the minimum temperature. Well, there's another way of doing this that's been done so often that it's described in our textbook. Let me see if I can get the equation number, 641 and 642. So equation 641 is the key equation for this problem. It says basically that P2 divided by P1, the ratio of actual pressures, is equal to a ratio of this nameless piece of R, doesn't really have a name, but it is located in our table A22. And so, but this is only valid for air and only valid for isentropic processes. So let's jump to table A22, And so here we're talking about this information in these last two columns. It's again for air only, and delta S equal to 0. In this footnote 1 right here, they're saying, okay, P sub R and V sub R data used in equation 641, the one I just showed, which was P2 over P1 is equal to PR2 divided by PR1. And these P sub R's are just like the H and the U and the S naughts. They're only a function of temperature. So let's go here and think about it for a minute. Where maybe I organize the data in a table. That sometimes helps me when I think through it. I have a state. I have state 1. I talk about the pressure. It comes in kilopascal at 100. And the temperature, I'm going to get rid of the degrees C and put it all the way right in Kelvin right away. It comes in at 300 Kelvin. All right. If I wanted, I could get the enthalpy. If I wanted, I could get S naught. Not as a subscript, as a superscript, not. Okay. If I wanted, I could get this P sub R. Okay. So I would look at this table A22. I would find my temperature line of 300, and if I wanted, there's the 300.19 kilojoules per kilogram for the H. I don't really need U. If I wanted, I could get the S naught, and then if I wanted a P sub R. The V sub R goes with this equation 642. I should just write it down. So it's like the V final divided by V initial for air undergoing an isentropic process is equal to the ratio of V sub R2 divided by the V sub R1, using the V sub R's, but they're not needed in this problem. So if I just strike this out, like not needed, really not needed, and actually we really don't even need this one because we can just use this information P sub R. Okay. So we look at our problem, and we have the jump back here, some information known. We can put in the 300.19 kilojoules per kilogram. I really don't need S naught, take it out. P sub R is dimensionless, and we can look up P sub R. It comes in at 1.386. Double check. Come back over here. 1.386. Very good. Now for state 2, we're first going to go isentropic. So I'll call it like state 2s, just like this. State 2s. And then we're going to account for the isentropic efficiency of the compressor. Sometimes you put 2 or 2 actual for the other state. Well, it jumps up to what pressure? 525. So both of these have the same exit pressure. You're going to be at the 525 kPa line for both state 2s as well as 2. All right. Because we know the two pressures, 525 and then 100, we're able to get P sub R1. We can solve for P sub R2. So here, P sub R2, maybe I should write it on the other page, or I'll do this. I'll put P sub R1 times P2 divided by P1, substitute numbers, 1.386 times the 525 divided by 100. That gives us a value of P sub R of 2.17. No, not that. 7.2765. That's P sub R2. So it's only a function of temperature, so we would look down this column until we found where it falls. It falls in between these two. And we've done a lot of interpolation. And we would just interpolate to get the temperature, which would be the temperature 2s, T2s. And if you do that, it's very close to 480. It's equal to 480.2 Kelvin. And if you want, you just take off the 273, so that converts to around 207.2. We'll drop it and just call it 207 degrees C. That's T2s. Now I did all the work on this second page, but we come back and we find that, yep, it's around 207 degrees C for that exit temperature. That's the minimum theoretical exit temperature. Okay. I should fill out this table right here, 207. This value, piece of R, was 7.2765. You can also interpolate to get H, and so H is 482.65. All right. Now we're going to use the isentropic efficiency as 90%. Okay, how do we use that? Well, we can calculate the work that the compressor would need if it was isentropic. That's just H2s minus H1. Well, we just calculate H2s, 482.65 minus 300.19. So it would require, for every kilogram that went through it, 182.46 kilojoules of work per kilogram of air going through. Well, we have an isentropic efficiency of 90%, so that the work the compressor actually needs is larger than the work the compressor, if it was isentropic, by dividing that smaller amount by the isentropic efficiency of 90%. So we find that the compressor work needed is 202.73 kilojoules per kilogram. All right. So to find the actual leaving enthalpy, it's the inlet enthalpy into the compressor plus the actual work added. So we find that this is, and I'm going to put it up here in the table, that it comes out at 502.92. So now we know that enthalpy is 502.92. We look back in our table to find where our H is around 502.92. It's very close to 503.02. So it's a little bit less. It's right in there. And that was 502.92. So we can interpolate between 490 and 500, between this value of H and that value of H, to find our actual exit temperature, and it comes in T2 actual is 499.9 Kelvin. Well, ignore the 499.9 and put that to be 500 Kelvin. T2 actual. Okay. And let's go back here. We did the interpolation. So this would be the 500 Kelvin. Take off 273, and you're left with the temperature 2 is 227 degrees C. Answer for part B. Right there. Because they wanted it not in Kelvin, but in degrees C. And then part C, we already did the work for this. What is that actual compressor work? Well, it's right here. We just rewrite it. W compressor actual is 20. Now I have a question. 202.73. Let's give it the 3 significant digits. 203. Whoops. 203 kilojoules per kilogram of air flowing through. So that's the answer for part C. Check. And then entropy generation. Okay, now we have a little bit more work to do. Let's do a second law analysis for that compressor. I need to scoot down just a little bit. And we find that, I'm going to change color, sigma dot equal to m dot times the S exit minus entropy inlet. So if we're really looking to calculate sigma dot divided by m dot, because look at the units, it's per kilogram of airflow, it's just S2 minus S1. Well, here it's S2 naught minus S1 naught minus our natural log of P2 over P1. So yes, we probably should have included that in our table. Let me try and do this. Just scoot that over, right? And put in the S naught column in kilojoules per kilogram Kelvin. That's the units. And we would go back to our table again and pick up this S naught at 300, 1.70203, and then we would do the interpolation right here to get the S naught, but it's going to be very close to this value at 500 Kelvin. So let's go ahead and put our values in just so that we see them. It's a 1.70203, and then doing the interpolation you would get 2.21932. So it's like a little bit of work. Got it? R 8.314 divided by 28.97 known, and we know our pressures, and so everything is known. Maybe I should, well, I'm running out of space, but basically the answer for part D is sigma dot divided by m dot. When you run the numbers, comes right in at 0.0414 kilojoules per kilogram Kelvin. That's the answer for part D. Now, before we leave this, I want to do this. I want to say, what happens if somebody would say, change up the problem and use not variable specific heats, use constant specific heats. So you would not use the table A22, you would just use constant specific heats. What it is I just took the same problem and said, okay, we're going to use constant specific heats. And here the K is given and the C sub P is given. Well, where did this K come from and this C sub P come from? Well, if we take a look at table A20, for basically air is right here, and you're given C sub P, C sub V, and K, and it's a function of temperature. Well, for our problem, we had our compressor. It was bringing in 300 Kelvin air and out 500 Kelvin air. Well, what's a good average temperature in which to evaluate our constant specific heats? 300 plus 500 divided by 2, 400 Kelvin. So if we come in here on a line of 400 Kelvin and we say, oh, there's a 1.395 for K and C sub P 1.013. That's where these values came from. Now somebody says, well, let's say I don't really know the exit temperature. I could have picked the values like 1.400 for K and 1.005. That would be basically a cold air standard analysis type of calculation, but it wouldn't be as accurate. These wouldn't be as accurate because the air is undergoing an increase in temperature through the compressor, and the average temperature isn't 300. The average temperature is a lot closer to 400. So it's pretty intuitive. If you're going to use a cold air standard calculation and you want constant specific heats, then what you do is get a good average temperature and evaluate your properties at that average temperature, and your answers will be very close. So what I want to do is not jump around too much, but this answer right here for the minimum theoretical temperature at the exit, 207. Let's take a look at what it was accounting for variable specific heats, 207, the same thing. How about the exit temperature? Counting for variable specific heat, so it was 227 degrees C. It's still 227. About the compressor work, 202 for constant specific heats, 203. A little difference, not much though. And then the entropy generation, 0.0414. Notice all of these are to 3 sig figs, significant digits. So if we come over here, it's a little different, 0.0414 instead of 0.0411. So there you go. So just slight difference on the third digit for those. But how do we make this calculation? Well, it's a very similar process. But when you have the S2 minus S1 and you're using constant specific heats, it's C sub P natural log of T2 over T1 minus R natural log of P2 over P1, and the textbook goes through a few steps. Let's say it's isentropic, and there's a few steps in here where you're doing algebra and rearranging, and you find that you can write T2 over T1 is equal to P2 over P1 raised to the power K minus 1 over K. And you say, where did that equation come from? Where is that in our textbook? Well, that equation is equation 6.43 in our textbook, and it's applicable for any ideal gas, not just air, when K is equal to a constant specific heats. A lot of times that's how they write it. It has to be an ideal gas. Don't use this for steam in the two-phase region or liquid or anything like that. It's when it behaves as an ideal gas, and S1 is equal to S2. It's isentropic process. Well, for this, what do we have? We have our inlet and exit pressure. We have our K's given. And we have our inlet temperature. You can calculate T2min. And it comes in Kelvin. And then you convert it to degrees C. And that's your answer. Now, let me outline the steps when you have this isentropic efficiency. Well, we said the isentropic efficiency was the compressor work, the minimum if it's isentropic, divided by the compressor work actual. Okay, and from the previous calculation, that's just H2S minus H1 divided by H2 minus H1. Well, if you have constant specific heats, you can replace the change in the enthalpy by a change in C sub P change in temperature, T2S minus T1, T2 minus T1. Well, what cancels? The C sub P's cancel. Okay, so what you have is the isentropic efficiency. You can rearrange this equation to get that T2 actual is T1 plus T2S minus T1 divided by the isentropic efficiency of the compressor, which was 90% for this problem. So we put in our 90%. We put in our temperature, T1, it's 300 Kelvin, T2S, which was whatever it was, I forgot now, 480 Kelvin, and then the 300 Kelvin, and you calculate then the T2 in Kelvin comes in at 499.9-ish, and then you convert that over to degrees C and you get the same answer what we had for accounting for variable specific heats. All right, so that's how you get the answer for part B. And the compressor work, it was right here. You find that the work compressor actual is that constant specific heat times T2 actual minus T1. And we just calculated T2 actual, T1, C sub P given, and you calculate this for the compressor work, 202 kilojoules per kilogram of airflow. Okay, what about the entropy generation? Well, here's their equation. We had sigma dot divided by m dot is equal to S2 minus S1, which is C sub P natural log of T2 over T1 minus R natural log of P2 over P1. And it's like, okay, we just did a lot of work to get the exit temperature. We do need to put it in Kelvin when we put it in this equation. So, and we had the T1, and we had the P1 and the P2 and the R and the C sub P, and that's it. And so you see the difference. It's a very slight difference, only on the third significant digit. So hopefully that was helpful. So you can solve this problem using variable specific heats or constant specific heats. The way this problem was set up, the two values of K and C sub P were given, but even if they weren't, you might need to try to find a good average temperature and then go into the table, and let's say the average temperature you assumed was 500. Well, then use this value of C sub P and this value of K, and you'll be the final results will be a lot closer to the variable specific heat calculations. With that, I close. Thank you for your attention.